Welcome to lecture 2. In this lecture I'm going to talk about mechanical equilibrium, and we'll be looking at a couple of examples where we apply what we learned in lecture 1 about torque. And we're going to combine it with what we know from a previous course on forces. So let's define what we mean by mechanical equilibrium. Definition goes as follows. A system is in mechanical equilibrium if the net force on the system is 0 and the net torque on the system is 0. So what does that imply? Well, let's see. If I've got 0 net force, so no net force, means all the forces cancel each other out. That means the system has 0 acceleration. Of course, it could be moving, right? We're not saying it has to be stationary. We're just saying it's not accelerating. So it could be moving with a constant velocity. And we're saying there is no net torque. Well, that implies there's 0 angular acceleration. So that means the rate of rotation of the system is not increasing or decreasing. It could mean that the system is spinning. It's just not speeding up in terms of the rate at which it spins. Right? It spins at a constant rate, that's fine. It's mechanical equilibrium. Sometimes to distinguish those two, right, this one is always called angular acceleration, but if you want to be very clear about it and distinguish them, you might call this the linear acceleration, because it's along a line, or the translational acceleration, because the system is being translated in space, which is itself a bit of a technical term. So we could call this linear or translational. So if you see those terms, they essentially mean the same thing. They mean the acceleration, velocity, and so on that you know and love from your first mechanics course. Angular acceleration, maybe rotational acceleration, well, that is changing the rate of spinning. And we'll come back to this in more detail and calculate what the angular acceleration is if the net torque is not 0. However, right now we're going to deal with a situation where it is 0. Now, it could be that the object is moving with a constant velocity. It could be that it's spinning at a constant rate. Either way, if it's neither one of those, we might call it, this sort of study of those kinds of systems statics. Make a little note here. Statics means mechanical equilibrium, or system, the study of static equilibrium. And static equilibrium is like mechanical equilibrium, except that both the velocity and the rate of rotation are also 0. So static equilibrium is mechanical equilibrium with the special case that it's not just the acceleration that's 0, it's also that the velocity is 0 and the angular velocity, which we write as little omega, is 0. This is the angular velocity. We'll come back to this as well when we talk about systems that are actually rotating and possibly changing the rate of rotation. Okay, so we're going to analyze situations which are in mechanical equilibrium, and I'm going to do 3 examples. We'll spell out what those are. First, going to look at 2 people carrying a canoe and how much weight are they each bearing on their shoulder. Then we're going to look at a hanging drawbridge. Maybe you can visualize some kind of medieval castle here. The drawbridge, you know, pulled up by heavy chains. We're going to find the tension in those chains. And then we're going to look at a leaning ladder. And we're asking, like it's leaning against the wall, we're asking at what angle could it lean before it would slide and fall to the ground. So let's look at those three examples. Let's start with the first one. Here is the first example we're going to go through. We imagine there are two people, I've called them Alfred and Seamus, and they're carrying a canoe. Now maybe the canoe is full of the camping gear or whatever, and we don't really care, but the whole thing has a mass of 120 kilograms. And we're going to assume this is 3 meters long. Now they're carrying it as shown in the picture, and we're going to assume that the mass is evenly distributed along the canoe. So it's really for like mathematical purposes, a long rod that weighs 120 kilograms. Our goal is to figure out how much each of the two of them is carrying on their shoulder. You can tell they're not doing this symmetrically, like Seamus is right at the end, Alfred is sort of in the middle-ish. So are they going to feel the same force on their shoulder? Is it different? Well, we're going to find out. So we're assuming they're going at a constant velocity this way, constant velocity, no acceleration. So it's mechanical equilibrium. Okay, so what do we have to work with? Well, we want to figure out what forces are acting in the first place. So let's do that. So this is fairly straightforward here. Alfred is pushing up. There's a normal force here. That's Alfred's force. Seamus is pushing up over there. And I'm going to draw them equally large. I'm not assuming that they are, but because I don't know yet, all I can draw is their direction. Right? I don't know which arrow I should be drawing longer, which one shorter. And then, of course, the reason they're carrying this thing, the reason they have to supply a force, is because this thing has a weight. And the weight, as we've learned in the last lecture, we can pretend it always acts from the center. Now the center, this is 3 meters long, so 1.5 is gonna be somewhere here. This is the weight. Okay. So the weight is known, right? Because the weight is mg. We know the mass. We assume this is on Earth, so that's known. So our two unknowns are the two forces. So what can we write down? Well, we know it is equilibrium, so let's write down what you know from previous mechanics courses. The forces have to cancel out. The forces, they're all vertical here. So up force is equal to down force. Right, this plus this equals this. Yes, these are vectors. I'm talking about magnitudes here. Up equals down. I think it's more intuitive to set this one up. Okay, now we know what this is, right? This is 120 times g is 10, so that's 1200 newtons. Okay, now we can't solve this because there are two unknowns, so we need something else. Well, let's use torque. Now the question is torque around which point? What's the pivot point? I mean, which way might the canoe tip? Now it turns out, because the canoe is not rotating, there is zero torque about any point whatsoever. So I could pick this point here, or this point here, or this point here, or this point here, or this. Pick any point along the canoe. And the net torque around that point as a hypothetical pivot is going to be zero, because it's just not rotating at all. So what are good choices to make? Now, if I pick some random point here, well, I want to have three forces that all create torque. I can do it, but, you know, maybe we can make our life a bit easier. So the trick is that you generally want to pick a point for your hypothetical pivot where there is a force acting. So maybe this one, or this one, or this one. Because by doing that, the force that's acting at that point is not itself creating any torque around that point, because it is right at the point. There's no distance from the point. If I ask about pivoting around this point here, then Fa itself does not supply a torque because it's acting right on the point. So there's no R, like R equals 0 in the equation for torque. So we really only need one of them to solve the rest of the problem. So we actually have choices. And you'll figure it out as you solve more problems. So there is a kind of redundancy of information. But let's just write down each of them. So I'm going to consider the torque around this point, and this point, just to show you what happens in each case. So torque around around Alfred, or where Alfred is holding it. So around this point, Fa does not contribute anything because it's just pushing at that point. It's not turning it one way or the other. So around this point, the weight is is clockwise, and this one is up. Let me see if I can color code this. So I've got mg times, what's this distance? 0.5 meters. Write it without units because m is mass, it'll just get confusing. We know we're working in meters. That's 0.5 from here to the center of mass. And that's equal to what? Well, it's equal to the counterclockwise torque, which is Fs times distances from here to here, 2 meters, times 2. Now, because we know mg, we can actually work this out right away. We'd find that Fs, Seamus, is carrying 0.5 times 1200, 600, 6 watt times 2 is 600, 300 newtons. And then I can solve the full problem right away. I could right away say that therefore, if this is 300, Fa is 900 newtons using the force equation. Use the force equation. Now, the problem is solved, right? If this were the exam, okay, or really just going to calculate, we're done. That was super easy. But let's just see what happens, or what would have happened, had I not chosen this point, but say the torque around Seamus. Seamus is holding on. So torque around S, just so we see what happens. Well, torque around Seamus, the weight is down, and the distance is 1.5 meters from this hypothetical pivot. And Alfred is pushing up, creating a clockwise torque, and his distance is 2 meters from Seamus. So in this case, we get that mg times 1.5, right, that is the distance of the center of mass from Seamus, that is equal to the force Alfred supplies times 2 meters between those. So now we can solve this, and we'd find right away from this is 1200. 1200 times 1.5 is 1800. Watt times 2 is 1800, 900. So we get the same answer, except we find them in the opposite order. And then, of course, the rest is it just follows again from the force equation. Now, we could also just have used, we could have used this one not at all and just use those two and solve between them. Essentially eliminate mg between them. We have found the ratio of those two. Of course, somewhere along the way we need to know the value of mg. Right. Alright, so the next thing we could have done is we could have picked this, the center of mass, as our pivot point. Remember, we could have picked any point at all. But most of them like say this point here, it has 3 forces creating torque. Whereas this point here the weight doesn't create any torque. If I'm here, then Alfred creates a clockwise torque and Seamus a counterclockwise torque. So let's say this. So torque around the center of mass. The COM, center of mass. It's a fairly common abbreviation. Well, on the left-hand side, I have Alfred. So Alfred is 0.5 meters from our hypothetical pivot. So FA times 0.5 is equal to what's going counterclockwise. Counterclockwise, Seamus is pushing, but Seamus is 1.5 meters away. So that's equal to Fs times 1.5. And again, you could have solved this, for example, in conjunction with this, or this in conjunction with, say, this. I mean, you'll need mg's 1200 newtons in there, right? The mass of the thing matters, the weight of the thing matters. But say you plug this in here, pick any two of them. Any two of those equations in conjunction with knowing mg is going to send you to the answer. So there's more than one way to solve it, and that's more often than not true in the case of mechanical equilibrium problems. And that is because, strictly speaking, there's an infinite number of possible pivots, and around all those possible pivots, the net torque is 0, because it's clearly not rotating around it. If you don't believe me, solve it. Solve for those forces and check what is the torque around this point or this point. Now, you choose. You'll find it's always going to be 0, if you did your math right. Okay, so now we're ready to move on to the next problem. Here is our next example. I'm imagining a drawbridge. I'm visualizing a sort of medieval castle here, right? And there's the moat down here, and a drawbridge goes across it. Now, to make my life easy, I'm going to assume that this chain that holds up the drawbridge is here touched at a height that is equal to the length of my bridge. So this is both length L and L. And I'm going to imagine that the bridge itself has a mass of 2,000 kilograms. You know, it's fairly heavy, solid wood right there. So because those lengths are the same, I can right away see that phi, this angle right here, is going to be 45 degrees. Just from the geometry of those two sides being equal, this being an isosceles right-angled triangle. Our goal is to find the tension in the chain and the normal forces acting here at the joint. We're going to assume that this end of the bridge is not touching the ground, so there's no normal force here. So let's draw the forces. So the first force we can definitely draw is, of course, the weight of the bridge, and that's acting right in the middle. Because we're assuming the bridge is uniform, which is a reasonable assumption. But the weight is right here. We know what the weight is because we know the mass, 2,000 kilograms. What other forces are acting? Well, there's definitely going to be a tension, right? How do I know that? Well, if I imagine the tension wasn't there, like the chain gets cut, then the bridge would not just hang like this. So there's tension here in the direction of the chain. Tension, let's call it T. Is that it? Well, can't possibly be it, because if there was nothing here, right, and you'd imagine the bridge would just sort of like fall down like this. That's of course not happening. The bridge has to be supported here. In fact, if you look carefully, you also notice that the support here isn't just vertical, it also has to be horizontal, because the tension is pulling the bridge to the left. So this wall here on the left is pushing back to the right, or else the bridge would sort of move to the side, right, if there was no wall in the way. So there's a normal force here. So we can think of this as maybe one normal force. It's sort of diagonal this way, or we can think of it as two normal forces. one like this, and one like this. Don't have to be equal, we don't know that. But I'm going to call those the normal force Fn that points straight up, and the normal force that points straight right. Maybe they're two components of the same force. You know, we could model it that way, or just two separate normal forces, one due to the wall, one due to the little ledge that I've drawn here. And our goal is to find the tension and to find those two normal forces. Now that's three unknowns, right? Do we have enough information for that? Well, let's see what information we can use. This situation is static equilibrium, right? Nothing is moving. So the net force is 0 and the torque around any point is 0. So let's start with the forces. Tends to be the easier one. Now the forces, analyzing the forces actually gives me two equations, because the forces are 0 both horizontally and vertically. Let's maybe start with the vertical. So forces, vertical. What do those tell me? Well, which forces are acting vertically? That normal force, the weight, and there's a component of the tension. So let's set up equals down. Fn up plus t sine or cosine. Well, I'm interested in this vertical component. That's gonna be sine of phi. Now, I of course know that phi is 45 degrees. So the sine of phi is 1 over the square root of 2. And then that's equal to the force down, the weight, mg. So this is not an equation in torque. This is an equation in the forces. The fact that the bridge as a whole is not moving up or down. The reason there's an angle here, it looks a bit like a torque, but it's just because we've taken the vertical component of this tension. So that gives us one equation. And of course we know what mg is. I guess I should have called it big M here, so I need to make sure I'm consistent. Big mg. 2,000 kilograms, so this is going to be 20,000 newtons, because g is 10. 9.8, I know. It is 10. Alright, what about the horizontal forces? What do those do? Well, they're going to add up to 0, left equals right. Now this is actually easier because those two forces, the weight and the upward normal force, they're just vertical. So it's just those two, and they're going to be equal to each other, right? The normal force to the right is equal to the tension, I guess the horizontal component, so that's cosine phi. And of course the cosine of 45 degrees is also 1 over root 2. Because 45 degrees is exactly when sine and cosine are equal, right? The opposite is the same as the adjacent. So can we solve this? Well, let's see. We've got two equations, right? I've got about three unknowns. This unknown, Fn up, Fn sideways, and a tension. So I could eliminate two of them, but it's not enough information. So we need to consider something else. We're going to consider torque. Now I've got again lots of options here. I could pick any point along the bridge. I could even pick a point that's not part of the bridge, like out here. Torque around this point out here. It's gonna be 0 because the bridge is not rotating around this point. Has no angular acceleration around this point. But of course we want to make our life as easy as possible. So I'm looking at this and I'm like, wait a minute, if I think about this point here as my pivot, I mean, first of all, it's fairly intuitive. It's literally the pivot point of the bridge. But also, more importantly, for my purposes, those two forces are acting right at that point. So they would not contribute any torque at all. But really, I would get an equation that just includes the weight and the tension. Hey, that's fantastic. I'll do that. So let's set it up. Torque around, what should we call this, around the joint. That's what we called it up here, this point right there. And maybe label this. I don't know enough about actual drawbridge construction to know how this is actually done. Would be interesting to find out. Okay, the torque around the joint. So those two don't contribute at all. The weight down, so the weight creates a clockwise torque, mg times, okay, it is straight down, perpendicular to the direction connecting the point of action of the force and the pivot point. So there's no angle here, no cosine or sine, but there's a distance half L. Right? It's half of the length of the bridge, so times L over 2. That gives me the torque. What's that equal to? Well, it's equal to the torque created by the tension, which is, okay, now I have to be careful. This is at an angle, right? This is not in the tangential direction. I've got this angle here, so might as well go with it. I essentially need the vertical component of this, the component of this that's in the tangential direction. Tangential in this case means vertical because the line between the pivot and where the force acts is perfectly horizontal. So this is going to be equal to T sine of the angle, and again we know this is 1 over root 2, just writing it out in case the angle, is different in a different scenario. Times, well, where does this force act? It acts at distance L from the hypothetical center of rotation, the hypothetical pivot L. Hey, that's kind of interesting because actually if I look at this equation, I can actually cancel out the L. I can just rearrange this one to get that the tension is equal to mg over 2, right? The L is cancelled out, times, so this is 1 over square root 2, so I multiply by square root 2 on the other side, right, to rearrange this. Now, what does this make? 20,000 divided by 2 is 10,000. Right, we have 20,000 up here. Oops, I keep doing little m's, should be of course be big m's. That's what I called it. Got to be consistent here. Anyway, 20,000 divided by 2 is 10,000 times square root of 2, 1.41 is about 14,100 newtons. That's the tension in this chain. It's a lot, but it's a heavy chain. Now, maybe if you actually visualize a real drawbridge, there might be not one of them, but two that kind of hold the bridge on each end, like one closer to us, one further away from us. Can't draw this unless I draw a 3D picture. In which case we just divide this number by 2. Right? I hope it's obvious. Okay, so now we've got a tension. If we were only interested in the tension, we would be done. Fantastic, great. Now we're not done because we want to find those other ones, but now that I have the tension, I can use either one of those equations to find either one of those. So let's do it. I'm going to have that Fn horizontal, so this horizontal normal force here is, well, I know it's T times 1 over root 2. Well, 1 over root 2, this was root 2 times 10,000, so that actually just comes to 10,000 newtons, right? I'm taking this and I'm plugging it in here. And what about this one here, the vertical support force here, the vertical normal force, Fn up? Well, that's according to my math up here, it's equal to 20,000 minus T sine theta, T times 1 over root 2, sorry, not theta, phi, sine phi. So again, this is just 10,000, 20,000 minus 10,000 is also 10,000. Coincidence? Perhaps to do with the even geometry, right? But here are our answers, 1, 2, 3. Could we have solved this differently? Yes, we could have done. We could have written down, say, the torque around this point here, in which case the tension up, the tension creating a counterclockwise torque would have had to be cancelled out by the torque created by those forces. Actually, the horizontal one doesn't create any torque because it's in the wrong direction, right? It's towards the center of rotation. So actually only this one would have contributed to this one. Could have solved it that way. We could have picked this point here as our pivot. Then we would have had the weight competing torque-wise with this one here. Again, we would have got an equation. Could have put the pieces together differently in terms of the algebra, but we would have found the same answers in the end. Alright, so that was the drawbridge problem. If you want to think about this, if you want to take this further, maybe we'll have time to do that in class. Imagine the drawbridge is being pulled up. Suppose the drawbridge is pulled up by some angle, not all the way, not 45 degrees, just some angle, maybe 30 degrees, like this. It's the same length as before, so you can figure out where would this point be, somewhere up here, figure out the geometry, figure out the angles, and figure out what is tension in the chain then. See if you can do it. For an arbitrary angle, this gets pulled up like this. Bridge is up here now. Hasn't changed its length. What's the tension in the chain now? Fun little problem to think about. You can do it. Alright, let's move on to the third problem, which is a ladder leaning against the wall. Here is the third example and the final example of this lecture. I am imagining a ladder that's leaning against the wall. Now the question is going to be, at what distance can I put the ladder on the ground before it slides and falls down? Right? You can imagine literally doing this. You take a wooden board if you're into a ladder, you lean it against the wall, and it'll stay, but there'll come a point when the bottom part is too far away from the wall, it'll start sliding and falls down. To make my life a little bit easier, I'm going to assume that this wall here is frictionless. Of course, real walls are usually not frictionless, but that way I'm only going to worry about the friction here between the ground and the ladder. I'm going to assume the coefficient of static friction here is given by the usual symbol μs. I assume it's known. So my goal is to find the maximum value of d that allows for the ladder to remain in static equilibrium. Not start moving, not start falling, not start rotating this way as it's moving sideways. I'm going to assume the ladder has a mass m. I'm going to work entirely symbolically in this problem. It has a length L. So how do I start? Well, one thing I can do, and this is not necessarily the only way to start, but I can say, hey, so really, maybe I can rephrase this problem. Maybe it'll be useful to rephrase it as asking to find the angle, let's call it beta, to find the smallest angle this can be, right? Because as the ladder moves away from the wall, beta is going to get smaller. The smallest beta can be before the ladder falls. Maybe that'll be a little bit easier, because I clearly know how beta is related to d, because in this triangle here, d is L cosine beta. Let me just write this down right here. D is going to be L cosine beta. So finding the smallest beta is the same as finding the largest d. Just rephrasing the problem, if you like. Okay, so but where do I start now? Well, let's start the way we always start. We draw our free body diagram, right? We draw the forces, and I should have said this perhaps earlier, in terms of terminology, when we draw our forces at the different locations, like where they act, we call this an extended free body diagram. So in the middle, right, we have the weight. And the weight is, of course, mg. What other forces are acting? Well, it is leaning against the wall. There has to be a normal force between the wall and the ladder. How do I know that? Well, you can always just imagine the wall wasn't there. What would happen? Right, it would fall. So therefore, I know for sure there's going to be a normal force. It's pointing this way. Now there's going to be a second normal force from the floor, so maybe I'll call this one F wall, the force due to the wall. Right, this one here. There. The other forces are going to be acting down there. So there's a force, a normal force, between the floor and the ladder. How do I know that? Well, if the floor wasn't there wasn't a normal force, the ladder would just start falling. That's a normal force upwards. I'm going to call this F floor. It's due to the floor. And then we said there is friction, right? Again, if you try this on a sheet of ice, it probably wouldn't work very well. You wouldn't get a very big angle at all. There's a coefficient of static friction here. Which way is that force? Well, if it wanted to slide, it would be sliding this way, right? The bottom would not be sliding to the right. That would mean the ladder would have to be moving upwards. So the ladder wants to move, this part of the ladder wants to move to the left. The force of static friction is going to be to the right. I don't know how big it is. Don't know how big the friction is. So those arrows, they really just show me the directions. I don't know what the magnitudes are yet. Okay, let's analyze this situation. Okay, so again, I've got forces in two directions, horizontally and vertically, so I'm going to get two equations from just writing down what I know about the forces. So let's write down the forces horizontally. Forces, I'm just going to do a little arrow left and right, meaning now in the horizontal direction. It's fine, you know what I mean. Now conveniently in this problem there are four forces, but they are thankfully all either vertical or horizontal, no funny angles. Well, horizontally I've got friction to the right, force from the wall to the left, so they have to be equal. Now I've abbreviated the force from the wall, but I haven't abbreviated friction, but who cares, right? I'm allowed to do that. And that's it. It's nice. What do we know about the forces in the vertical direction? Well, again, there are only two of them, so those better be equal. If the wall was not frictionless, then the story would be different. There'd be a third force here, a friction here, we'd have to think about it. Not in this case. So the force from the floor upwards is equal to the weight equal to mg. Alright, that's easy enough. Very simple equations. Now, this is not enough for me to actually solve this. So, because all of those will be true for any angle, like there's no depends on the angle yet. So let's consider now the torque. Now the torque around what point? Now I have a bunch of choices. I have an infinite number of choices, strictly speaking, but only a few sensible choices. Now I see, hey, there are two forces acting down here at this one point. If I make this the pivot, then I only have to worry about the torque created by those two forces. Right? Because both of those would be acting right at the pivot point, therefore contribute zero torque. So that's what I'm going to do. And I'm not sure if it's going to get me to the answer, but maybe it will. If it doesn't, okay, well, I can consider a second point. But let's work with this first. Let's try to keep our life as simple as possible. So I'm going to consider the torque around the point down here. Torque around, what should we call this point? Around, I guess, point of contact with the floor. It's a little bit awkward, but that's okay. So what do I get for this one? The torque around the point of contact with the floor. Well, I have to think about the angles here. That's a little bit tricky. So this angle is beta between the ladder and the horizontal, which means by Euclidean geometry, right, this angle is also beta up here. What about this one? Well, so this one here would be 90 minus beta, but maybe I want to try to work just with beta. So I'm going to draw a line like this, and then this angle here is also beta. Right, so because this angle is 90 minus beta, this whole thing is 90, so this must be beta again. Alright, so can I work with those angles? Let's have a look. So the torque clockwise, right, is going to be the weight, which is mg. So let me write this down. So clockwise equals counterclockwise. Just so I don't get confused what I'm doing. Right, the torque in, oops, you can't even see this. Now you can. The torque in this direction, the torque in the clockwise direction, is equal to the torque in the counterclockwise direction, in terms of magnitudes, of course. So what is the torque in the clockwise direction? Well, around this point, the only thing that tries to pull the ladder in this direction is the weight. It's going to be mg times, I only want the component that is essentially along this dashed line that I've drawn, right? I want the component that is tangential to the radial line between the pivot and the point of action of the force. So this means I've got to take the adjacent of this, so it's going to be cosine beta. If you're not sure about this, if this sounded all a bit strange to you, pause the video right here and make sure you understand why I'm taking the cosine of beta and not, say, the sine. Where is this force acting? Well, the distance from the pivot point is L over 2 because the weight acts bang in the middle. Alright. Now what's that equal to? It's going to be equal to counterclockwise torque, which in this case is just the torque created by the force on the wall. And in this case, from the geometry, you can see I kind of want the tangential component here too, so in this direction, which is the sine of beta. Right? If you look at our initial definitions of torque, our mathematical expressions, if I have this angle, it's the sine, and it's clear from the geometry why that is. Right? It is not just drawn out of thin air. I want the component of this that's in the tangential direction. I could take the cosine of this angle or the sine of this angle. It's going to be F wall times the sine of beta times where is it acting? Oh, it's a distance L, like the whole length of the ladder away from that point down here. So times L. Color coded this so you can see where each of those two sides came from. Now let's simplify it. I can cancel out the L, which is interesting, right? Being able to cancel out the L tells me right away that the length of the ladder does not affect my answer. Right? It is mathematically convenient to be like, hey, my equation becomes simpler. Great, right? Fantastic. But also there's physical meaning in being able to cancel out something completely. It's telling me the length of the ladder has no effect on how far away from the wall I can, well, strictly speaking, it's going to come back in here, but it doesn't affect the angle. Right? Of course, for the distance from the wall, that itself depends on the angle and the length. But the angle you're going to find, beta, does not depend on L, because that's cancelling out right here. Okay, so where do we take this? Well, what do I know, what do I not know? I can, let me just rearrange this a little bit. And what I'm going to do is I've got the force on the wall, I don't know what it is, but I know it's equal to friction, so I can replace this by friction. Right, so this here is equal to friction, which I know from up there. So now I can rearrange this, and I'm going to get that the friction is equal to, so let's have a look. mg over 2. And then I've got cosine over sine, but sine over cosine is tan. So this is divided by tan beta. And so the force of friction is going to be equal to this. If the ladder is not falling, the force of friction is equal to this. Now what do I know about the force of friction? Well, I know that the force of friction is always smaller or equal to the coefficient times coefficient of static friction times the normal force. The normal force is of course this one here. And I know what that's equal to. It's equal to mg. Okay, so let's put those pieces together. I therefore know that this is equal to this. At the limiting case. This is going to be smaller or equal to this, but at the limiting case, right, friction is at its maximum. So let me write this down. I'm going to have that mg divided by 2 tan beta is smaller or equal to mu s times mg. Now that's nice. I can cancel out m and g. Interesting. What does that imply? Well, I mean, again, it's nice algebraically, but also it tells me that the mass of the ladder has no effect on at what angle it's going to slip. Also, g doesn't matter. It doesn't matter if I try this experiment on Mars or on the Moon or anywhere else. As long as there is some gravity, I'm not floating in the middle of space, right? I can't do it there. But as long as some gravity, so g is not 0, as long as that's true, my answer is going to be the same, right? So I've got that 2 tan beta is smaller or equal than mu s. So 1 over 2 tan beta, excuse me, smaller or equal to mu s. So what does that imply? This implies that, I guess let's rearrange this, tan of beta, which is going to be a positive number because beta is between 0 and 90, is greater or equal to 1 over 2 mu s. Now if I know the value, I can plug it in. I can find beta by taking the inverse tan, and I can then finally find that the distance d. Of course, I'm assuming equality for the limiting case. Right? Equality here is that point where it's just about to slip, but not quite. But if you make the angle the teensiest bit smaller, it's going to slip. All right, that completes the problem, right? I trust that you can actually fill in the last few details here that I only talked about and did not work through in all the glorious detail. So those were 3 good problems to practice, right? Again, maybe you could now you've looked at them, I've done them for you. Can you turn off the video and rework those problems from scratch yourself to make sure you've actually understood it, you've actually absorbed those techniques, you ingrain them in your brain of how to deal with those kinds of situations. That is what I suggest you do. All right. Thanks for watching. This was lecture 2 on mechanical equilibrium, and I'll see you in the next lecture or in class.